Welcome to Astronomy, Chapter 16. In this chapter, we're going to be taking a look at galaxies as a whole, meaning all of the objects that we can see that we classify as galaxies in the known universe. Now, this chapter is going to be a bit of a brief one because as we get towards the end of the course here, we continue to get a little bit more vague, a little less specific about the information we know about these objects, simply based largely off of their distance. They are so incredibly far away. But the first thing we're going to look at is the types of galaxies. And if you remember my analogy from earlier that I mentioned last chapter and as well way back in chapter 1 with the idea of a galaxy being like a city, if you think about that, there are lots of different types of cities. You have some very large, massive cities with large, big, metropolitan centers. And then you have some, towns that are small and you barely can tell that they're a town when you go through them. Galaxies are much the same way. It turns out the Milky Way is a very large city and is a large spiraling galaxy. And when most people think of the word galaxy, they usually think of a spiral galaxy, shown for you on page 488. Now, as it turns out, there's actually several different types other than spiral galaxies. There's also Edwin Hubble, who classified these, broke them apart into barred spirals, meaning they have a bar in the center, and we'll look at some of those. Ellipticals, irregulars, and then a variety of subclasses underneath each one of those headings. And basically, the idea here with the spiral galaxies is talking about the relationship of the bulge of the center, how much mass or how much stuff is in the center of this thing, is related to how tightly those arms are wound. So we would see, for example, M104, which is more affectionately known as the Sombrero Galaxy, would be a tightly wound galaxy if we could see it that way. We don't see it that way because instead of looking at it like this, we look at it like this, so we see it on the edge. The Sombrero Galaxy, though, is a beautiful view as it's Messier, Messier object number 104. And they give a couple of other examples there of weakening centers related to their arm spirals. And they show this again a little bit further in the on page 490. This being an object, they're showing it to you in the ultraviolet part of the spectrum. Excuse me, the visible part of the spectrum, showing you that these arms are this rotation is what's curving this material around, and that is an essential part of understanding gravity. That gravity is the role of these galaxies. That is that this object is spinning, and like everything, virtually everything we see in the universe, on the big scales, it tends to be going around in relative circles, not in perfect circles, but it is rotating around something. Galaxies are no different. What I highly recommend you look at is page 493. 493 really dissects very well the different parts of a galaxy and why we see them doing what they're doing. So as you're going through your reading on this, I recommend you look at what's in these things and look at the different parts of how we think these pieces are put together. Now, observations allow us to do a lot of useful things in terms of figuring out what's in these galaxies, in terms of how fast is this thing spinning around, what are the different types of stars out here, and based on what we know about stellar evolution from back in the third unit, we can make pretty good conclusions about what is happening inside of this, what they call a grand design spiral galaxy. So this is an excellent graphic. I highly recommend you look closely at page 493 when you're going through this. Now, after we see that, they give you a couple of barred examples. The bar just means that as if there is a object that is horizontal or non-curved in the center near the galactic nucleus, and it is spinning around this entire barred area, not just around the nucleus. But nonetheless, after we look at our spiraling galaxies, there's also a huge number of galaxies that are called elliptical galaxies. And elliptical galaxies are, if you showed someone a picture of this, and you said, what is that? Very few people would recognize that as a galaxy. It looks like a star. It looks like a big blurry star. And in fact, it took a tremendous amount of effort to realize that these are actually other types of galaxies. If you want to think of my analogy on the city thing again, if these are our big metropolitan cities, the Chicago, the Houstons, the New Yorks of the world, these are a smaller, less well-defined areas. These could be thought of as like our smaller towns. Now, they're not necessarily small per se, but they are a different structure to them. And what I mean by that is to say, a lot of small towns don't have the same features of a big city. A lot of small towns don't have an airport. A lot of small towns don't have certain restaurants or certain, shopping areas that a big city would have. So it doesn't have some of the same features. And by features, I mean these big swirling arms where we can see this well-defined area. They just have different features to them based off of what they're made out of. So elliptical galaxies are different, significantly different. Then, after the ellipticals, we actually have another classification that is sort of the other variety, is called an irregular galaxy. And irregular galaxies are actually very difficult to identify they're a galaxy at all because they have an unusual shape. Probably the most well-known is the LMC. The Large Magellanic Cloud is an irregular galaxy that does not have a well-defined shape. It is not in an oval shape, and certainly does not have these swirling arms associated with a spiral galaxy. You should also take note of the tuning fork diagram. The tuning fork diagram gives you sort of the breakdown of the different styles of ellipticals, from slightly elliptical to very elliptical. It gives you a breakdown of the spirals, from tightly spiraled to loosely spiraled, and from tightly barred to loosely barred, and then also the irregulars. And they do also talk in here about something called the lenticular galaxy, which you need to make sure you read about as well. Now, I'm talking about in 16.6, the lenticulars. Okay, moving on. If we're talking about galaxies, we also need to talk about clusters of galaxies. And again, I'm referring to my analogy on this because I think it works. If you think about cities, cities have a tendency to grow. First off, they get bigger. Most cities do. They tend to get bigger. But the big cities have a tendency to draw in more cities. Once an area gets large, it has certain attractive areas based off of population and commerce and more jobs. And so if you have more jobs, more people move there. When more people move there, they bring in more income, and that income turns into more jobs, and it sort of continues to grow and grow and grow. And sort of cities end up taking over other cities. And they end up forming this big globed area. A great example of this is the Northeast United States. The Northeast part of the United States has become sort of this major metropolitan area that lasts for a great distance up and down the eastern seaboard. We also see this other effects with large cities where they have where there used to be other towns that were sort of outside of the city, and then the city sort of ends up growing into them. But the idea here is what I'm talking about is with galaxies is I'm talking about clusters of galaxies. All right, galaxy clusters happen because of gravity. The gravity is pulling these things together. There's an attractive force holding all this together. Gravity has been, the thing we have talked about since the beginning of this course. And here we are all the way at the end of chapter 16 talking about how these galaxies have a tendency to join one another. Now, what is a cool picture on page 1616 is the superclusters in our neighborhoods. These are the clusters of galaxies around us. So this is like looking out your window and seeing all the other cities that are around you. Or perhaps, this is like saying, what are all the cities in the state of Kansas? Or what are all the cities in the 4-state area? Very cool thought to think about. All of those put together. But those are what form our galaxy clusters. And what we know about these galaxy clusters is they have a tendency to combine with one another, which I kind of touched on a little bit earlier. And then they give you all sorts of these beautiful descriptions of showing you where we see these things happening in the universe. So it's an exciting part of what's going on with astronomy. Now, speaking of what's exciting with going on with astronomy, especially in the area of research right now, is this idea of dark matter. Now, I talked about dark matter with last chapter, talking about the idea of the missing mass in a galaxy. Turns out there also appears to be missing mass in a cluster of galaxies. So the idea here is if we have a cluster of galaxies, we see all of them moving around, we can measure their speed relative to one another, and they appear to be having a significant amount of matter that is missing as well. So, again, with the dark matter concept, of course, it emits no radiation, no light that we can detect in any way, but yet what we understand about gravity tells us there has to be some more matter there. And that is one of the great areas of research right now, is what's going on with dark matter. And galaxy clusters indicate that this is going to need some more research as well. Now, the last thing that I want to talk about in this chapter is on page 507 and moving forward, is talking about the idea of red ships of superclusters. This is a fascinatingly exciting part of our study here in astronomy. And that is the idea that when we look at these star clusters, not even star clusters, when we look at these galaxy clusters and galaxies in general, we see one consistent trend. And the trend is this: the farther away the galaxy is, the faster it appears to be moving away. Now remember, way back when we talked about the Doppler shift, when we measured light, how it can be blue shifted or red shifted. And what we see with these galaxy clusters is they appear to have red shifts that show us how fast they're moving away from us. Now, here's where it gets really mind-blowing, because we thought for the last at least century and a half that if there has been a Big Bang, which we'll talk about this idea of the start of our universe, if there has been one moment of our universe starting, one initial point where it all was created and it all got going, then if it was all just shot out from that spot, that everything eventually should be slowing down, and eventually the end of that hypothesis was called the Big Crunch, that everything will come back together. Eventually, many billions of years later, this is going to happen. It now appears that part of the hypothesis is almost certainly totally wrong, because we have found out that not only are our galaxies expanding, but they are increasing at the rate at which they are expanding. Very, very peculiar thing has happened with that, because this was completely not expected for us to figure out, to find out that not only are they moving away, but they are increasing at how fast they're moving away from us. That means, based off of the most fundamental laws of physics that we understand, something must be pushing them. We have no idea what that is. The push is what we call dark energy. There's some energetic force. We have no idea what it is. We can't see it. We can't detect it, but it's pushing these things out. And certainly that is another area that we're going to be studying in great detail as the years pass in astronomy. One of those two, dark matter and dark energy, are really hot topics in terms of trying to figure out what's going on with our universe. And they show up nicely here in the reading when you're going through 507 through about 509. Oh, and the other thing I want to mention, make sure you take a look at 508, a huge important concept. I can't believe I almost missed this. It's called the Hubble Law. Got to talk about the Hubble Law. The Hubble Law is a way for us to measure, to quantify the rate of this expansion. And if we can quantify how fast it's expanding, and we know how far away it is, we can do a smidgen of math and figure out then how long has it been expanding, thereby saying what is the age of our universe. And so the way that we end up with numbers like our universe is 14.6, do they give us the exact number in this section? It's 14 billion and some change. Looks like it doesn't give it to us, but the number ends up being like 14.5 billion years old, and it is based off of this measurement, what we call using the Hubble Law. And the Hubble Law is trying to say, as things get farther away from us, they're moving at a faster rate, and so what we can do is a little bit of basic math to tell us how long they must have been moving away. So if we work backwards, that is, when were they all together? That is trying to give us a way to get some insight as to when our universe would have started. And of course, we have to remember that with that idea, all of that is contingent on one belief that everything is moving as it always has been. And of course, we have no idea to know if that's a valid argument or not, but we don't see anything to the contrary. So this is sort of our best guess. The Hubble Law gives us a way to give a best guess as to how long our universe has been expanding. Currently, the measurement is somewhere around 14.5 billion years is where that comes in at. So when you're going through your reading on chapter 16, you'll notice that that law, that's an important part. Make sure you're keeping up with the reading. Take a look at the PowerPoint, and you should be ready to go for the homework assignment for chapter 16. Good luck.